I think we might be able to go ahead with it as well. Yeah. Okay, so let's start then. Again, good afternoon and good morning to everybody, and welcome to the Energy System Planning for Sustainable Development in Thailand, the webinar series 1 on the energy optimization, modeling, and investment strategies for generation, transmission, and distribution, which is co-organized by the Joint Graduate School of Energy and Environment, King Mongkut University of Technology, Thonburi, under a collaboration with USAID Southeast Asia Edge Hub, implemented by Tetra Tech. Before I move to the session, I would like to remind you about some the housekeeping matters, as you can see on the slide. So please mute your microphone during the webinar. We have the Q&A session after the presentation, and you can ask the question by typing in the chat box, or you can raise your hand by clicking some icon, and then you'll be invited to ask the question directly. And this webinar will be recorded and posted on the JGSCE website and the Facebook JGSEE CEE. Okay, so here is the agenda. But before going to that, I would like to make a bit of introduction about this webinar. So during the past years, the JGSCE, with the strong support from USAID Southeast Asia Edge Hub, has carried out the capacity building and knowledge sharing activities. One of the key activities is the development and launch of the energy modeling and analysis course, which was structured to include the energy and power system modeling from the demand to generation, transmission, and least cost optimization through PIPSA, or the Python for power system analysis. And finally, the holistic energy system planning. The energy system optimization modeling is a powerful tool that can help policymakers and planners make informed decisions about design and operation of the energy systems. So this webinar aims to highlight the importance and benefit of energy system optimization modeling to energy policymakers and planners, and the key tools commonly used. So this webinar features expert speakers from Thai power utilities and from Tetra Tech, who have extensively been working with power system operation and modeling. And so next in the agenda, I would like to invite Professor Nawadon Lausiripot, the director of the JGSEE, to give an opening remarks.
Okay, so first, thank you very much, Dr. Smilat, for the nice introduction and also arrange this interesting webinar. So good morning and also good afternoon, distinguished speaker and participant. So I'm Nawadon Lausiripot on behalf of the Joint Graduate School of Energy and Environment. It is my great pleasure and honor to welcome you all to the webinar on the energy system planning for sustainable development in Thailand. Ladies and gentlemen, I think we all know about the importance of the global warming awareness at the moment, because now the world current effort on the energy and environment are mainly to transform the energy system to achieve the target on the carbon neutrality and the net zero emission target, as Dr. Sumit mentioned already. And recently, there are several attempts, and the share of the renewable energy in the electricity generation has been increased progressively. because of the a lot of the policy implementation, regulation, incentive, and innovation embedded in the power system. Okay, so when we talk about innovation, at the moment, several science, technology, and innovation relevant to the cleaner technology has been developing progressively. Okay, and one of the important example like the innovative technology and the smart solution to control and to manage the energy system with the higher sharing of the renewable energy integration, with still enabling to reliability and stability of the overall energy system with good example. So I think in the near future, a lot of the advanced digital technology such as big data analytics, the Internet of Things, and the artificial intelligence will be certainly be applied and to accelerate the transformation of the energy industry. So in this webinar, okay, we are going to introduce you the energy system optimization model, okay, which is very powerful tool for the policymaker and also the planner to develop the effective strategy for achieving carbon neutrality and also other energy related objective. So you have chance to learn a lot with this relevant topic from the expert like from EGAT, PEA, and also USAID Data Tech. So once again, welcome you all to this webinar, and I do hope that you will find this webinar useful with a lot of the take-home value. Okay, so thank you for your attention.
Okay, thank you very much, Professor Nabadon Laosiripot. So now I would also like to invite Ms. Amanda Wadendu from USAID Regional Development Mission for Asia to give an opening remarks. So Amanda, please. Yeah.
Thank you very much. Thank you, Dr. Sunarat and Dr. Navadol. Good afternoon, everyone. My name's Amanda Vanden Doel, and I'm the Sustainable Energy and Safeguards Lead for USAID's Regional Development Mission for Asia, based here in Bangkok. And on behalf of USAID, I'm honored to speak at this webinar today on energy optimization modeling. We're very proud of the partnership that we're sharing between USAID and King Mongkut University of Technology Thonburi, or KMUTT. Our relationship began in 2021 with KMUTT signing a memorandum of understanding with the USAID Southeast Asia Edge Hub activity. And I'm thrilled that KMUTT is also developing a relationship with another USAID funded activity, the USAID Southeast Asia Smart Power Program. Since the MOU signing, we've seen increasing amounts of collaboration, including KMUTT's participation in a webinar on the role of increased hydrogen production as a low carbon alternative to fossil fuels in Southeast Asia. USAID was also honored to serve as guest speakers for a KMUTT Joint Graduate School of Energy and Environment training program with the Thailand International Cooperation Agency on addressing best practices for low carbon cities. We were privileged to have KMUTT's participation at a USAID event on air quality to highlight the university's scientific research and policy recommendations. The USAID and KMUTT JGSEE partnership also includes a student internship program for KMUTT JGSEE graduate students to actively take a role in USAID-funded energy programs here in Thailand. More recently, USAID coordinated with the graduate school to design and co-teach the university's graduate level energy modeling and analysis course. The objective of this ongoing course is to familiarize graduate students and faculty with tools for energy planning and analysis. 17 students are enrolled in the 4-month course that will end next month. I couldn't be happier with the progress that we've made together. The relationship with USAID and KMUTT that we've built is perfectly in line with USAID RDMA's Regional Development Cooperation Strategy. That strategy was founded upon the US vision for a free and open Indo-Pacific to enhance economic prosperity and ensure peace and security in the region. USAID RDMA is dedicated to partnering with regional organizations to address transboundary challenges and strengthen energy systems. Today, we will discuss the importance of energy modeling for energy policymakers and planners. However, even if you are a distribution engineer working to provide individual households with an electricity connection, or a chemical engineer working on extracting greater efficiency from a new ammonia power production plant, the knowledge and understanding that energy systems modeling provides is applicable and beneficial. An energy systems modeler needs to have a keen eye and to understand that decisions made today impact future society, from policy to investment. Energy modeling can help ensure that Thailand's energy systems are low cost and resilient to the impacts of climate change, while identifying a clear path to reducing harmful emissions. Using energy modeling tools can help drive the clean energy transition. This is why USAID is dedicated to helping upskill academia. Technical universities like KMUTT are often tightly integrated with industry, and are seen as trusted advisors to engineers, policymakers, and planners within the workforce. We believe this energy modeling course and the webinar today will assist in elevating KMUTT's ability and the ability of all of those who participate to collaborate, providing a new pathway for Thailand as it strives to achieve carbon neutrality by 2050 and net zero greenhouse gas emissions by 2065. Thank you for taking part in this webinar today. I look forward to hearing from our esteemed panelists from EGAT and PEA on the successes, challenges, and barriers for generation, transmission, and distribution networks, and how Thailand can benefit from using energy system modeling. And on behalf of USAID, I hope to see the USAID KMUTT partnership grow and flourish in the coming years. And I look forward to expanding relationships with all of you taking part today. Thank you.
Okay, thank you very much, Ms. Amanda Van Den Du, for your speech. Before we start the technical sessions, I would like to ask all the speakers and the participants to turn on your camera so that we can have a group photo. Okay, I would like to ask the staff to also give us some signal that you take the photo.
Okay, 1, 2, 3. Just a moment. I need one more. Okay, 1, 2, 3. Thank you very much.
Okay, thank you very much ค่ะ คุณสิริยา So now we are ready to start the technical session. So today there will be 4 presentations from the 5 distinguished speakers, 2 featuring the status and planning for Thailand power systems, and another 2 presentations from the international experience on power system operation and expansion. So for the first presentation is Mr. Konkiat Jalern Pacharakit from the Electricity Generation Authority of Thailand, or EGAT. And he will present on the topic, the EGAT investment strategies for generation and transmission expansions, the challenges and barriers. So Mr. Konkiat, the next 30 minutes will be yours.
Okay, good afternoon, everyone, and good morning. It is my pleasure to be here today. I would like to present EGAT investment strategies for generation and transmission expansion, challenges and barriers. Next slide. And here is the outline of this presentation. Next slide. Yes. In this slide, We start with the carbon neutrality. Why the world is dealing with the increasing violence of climate change. Many countries have set goals to reduce greenhouse gas emission seriously. The goal for Thailand to achieve carbon neutrality by the year 2050 and the net zero gas emission in greenhouse gas emission by the year 2065. And the main policy direction in Thailand to achieve the carbon neutrality, such as to increase the share of RE to above 50%. Secondly, to increase the energy efficiencies to more than 30%. Third, to promote EV according to 30 at 30 policy, which is produce the zero emission vehicle at least 30% of the total automotive production within the year 2020. And the fourth is to restructure of energy industrial according to the 4D 1E guideline, which composed of 4D composed of the digitalization. That means to accelerate the upgrade the existing grid to be a smart grid to accommodate more electricity generated from RE. The second D is decarbonization to promote power generation from RE, such as solar, wind. The third D is decentralization to support transmission electricity through transmission system to support, I think it's to support or facilitate trading between prosumer. And the last D is the deregulation to open the specific area for the prosumer to can trading the power. We the regulator should be deregulation some for the startup business. And the last one is mean electrification, that to expand the EV and promote the use of EV for the electricity generation industry. For example, to increase share of RE, to develop carbon capture, utilization, and storage technology, to develop the carbonization and smart grid, to implement platform and data center to control RE. Next. For the ECAT, carbon neutrality policy, ECAT with the main mission related to power generation. ECAT has announced the carbon neutrality by 2050 policy to support Thailand clean energy transition. ECAT aims to realize the net zero carbon dioxide emission with the triple S. The first S is the source transformation. It means increase the RE share in power generation mix and use modern technology for clean energy, such as green hydrogen. Second S is sink co-creation, such as reforestation and carbon capture utilization storage. The first the third S is support measure mechanisms such as any efficiency project and BCG economies. Next slide. Yes. Next slide, we talk about the Thailand PDP 2018 Revision 1. This slide shows the information about Thailand Power Development 2018 Revision 1. First is all Thailand PDP are considered based on three main points. The first is the national energy security. For the energy security, we consider the security of each region or of each area. Second, the distribution of power generation fuel or the generation sources. Third is the reduce of dependence on the natural gas and increase power system flexibility. The second point is the economy. The electricity price is reasonable to maintain the country economic competitiveness and to support the local economy such as the community power plant. For the third is the ecology. Increase power generation from RE, promote energy efficient conservation measures and demand response and smart grid development. Next slide. And it can have a power purchase from Lao PDR to realize the carbon neutrality. It has committed to purchase electricity generated from hydropower plant in Laos, PDR, namely Luang Prabang hydropower plant. The capacity is 1,460 megawatt. Schedule commercial operation date in 2030. And the second project is Pak Lai hydropower plant. The capacity, the installed capacity is 770 megawatt and SCOD on 2032. The third project is Pak Beng hydropower plant, 912 megawatt, SCOD on 2033. And the last project is the Sekong 4A and 4B hydropower plant. The capacity, the installed capacity is 355 megawatt, SCOD on 2033. The total hydropower plant from Lao in the near future is 2,497 megawatt. Next slide, yes. Next slide is the hydro floating solar hybrid system. According to PDP 2018 Revision 1, ICAT has planned to increase the share of the renewable energy in electricity generation to 30% by integrating renewable innovation so it can generate electricity consistency and stability, leading to the development of the 16 hydro floating solar hybrid projects at ICAT existing dam with the total capacity of 2,725 megawatt, which will begin commercial operation within 5 to 10 years. And the figure left figure to show that is the Silinton Dam of the 45 megawatt hydro floating solar hybrid project. This project have This project began commercial operation on October 31st, 2021. And next is the Umolat Dam. Is the 24 megawatt project of the hydro floating solar hybrid project also. Next. This slide tell on March 33, 2033, the NEPC have approved ECAT transmission system project. This project is for accommodate the RE according to this PDP. And this month on April the 5th, 2023, ERC approved the 175 projects of clean energy generation. Total amount of 4,852 megawatt. This project is the private project. Next. And this is the transmission system to accommodate the RE project in the PDP 2018. The first is the transmission project for the upper northeastern region, TIPN. This to accommodate the RE project that will install at the northeastern region. For the second TIEC, that is for also for the northeastern, but the lower northeastern, but the lower north and central part, or some Bangkok metropolitan. And the third project is TIS. This is for the southern region, the RE project in the southern region. And the figure of the cost and the construction progress you can see on the slide. Next. And this is the last ECAT challenge and barriers. The first challenge is the power system flexibility. This means due to ECAT have no idea about the location of the project, such as the wind project or solar project, VRE projects, to prepare the equipment to the suitable for the location of the VRE project. Is a challenge. ECAT to plan to install the power system flexibility plan. And the second, the operation of the future grid. The operation of the future grid, it means ECAT should prepare the such as the RE forecast center and demand response center for security and efficient power system operation. And the third is power grid infrastructure. The difference between power system flexibility and power grid infrastructure, it means power grid infrastructure is planned to accommodate the capacity of RE capacity that issued in the PDP 2018, that only accommodate the capacity, not for the stability, but for the power system flexibility is for planned for the stabilize the system because we don't know where the power plant installed. For the third, market design for carbon neutrality. Because now there are no clear policy and regulation leading to implementation process of the carbon neutrality market design. It is also under the study phase. Yes, that is the end of the presentation. Thank you very much.
Thank you very much ค่ะคุณกรเกียรติค่ะ I think we are still have some time. I think it will be okay to allow some questions to ask now as well. If not at the end of all presentations, if anyone have any questions now, we can ask as well.
Ajahn Sunirat, the chairman, may I have some comment about this plan?
Yes, please. Please also introduce yourself so we all know.
My name is Mr. Jamnong Sorapipat. I am the ex-chairman of Energy Division at JGSEE, but now I'm retired. According to your slide, I think this is very great. I would like to very great ambition and very challenge. But I still think that in this plan, probably you have say something about it, but it haven't yet in details yet to happen yet show to us. I think the missing information from ICAT is about the demand side management and energy conservation. I think this is in my opinion, this should be the first priority in order to help your objective to make everything overcome the barrier that you mentioned. Because for example, now we have the problem at the peak load. So the peak demand management to cut off the peak, which generally happen only a few days in a year. And so the concept of the peak demand management as well as energy conservation to suppress those increasing demand of electricity consumption every year. For example, the consumption of the electricity from household because of increasing of housing and the housing envelope have not yet been fully follow the guideline of regulation in order to conserve the demand of air conditioning road system, something like this. This is just an example. So I think, in my opinion, I think this should be give peak demand management and energy conservation for the demand side management should be the first priority in order to put into the power development plan in order to achieve the carbon neutrality and also as well as flexibility of the system. This is my opinion. That's all. Thank you very much for your listening.
Thank you very much ค่ะอาจารย์จำนง That's why I'm familiar with your voice. Yeah, may I askคุณกรเกียรติ to respond to this? Yes, please.
I think so far the demand response on the conservation in energy. The demand response, I think the plan for ECAT is the demand response control center that is the the consumer. I think is to promote this DSM. I think to consumer is. I think we can implement this for the only industrial consumer. For the residential consumer, is very difficult. Maybe cost for the consumer for demand side management, but very safe for the industrial consumer. I think that because the demand side is maybe you can make you for the road. If you can make the demand aggregator and control the use the demand electricity demand period, you can control the amount and the period of the use period, the utilization period. That it will save your money because you can you use the amount at the system maybe that is some to reduce the congestion of the system, and I think it depends on the. I would like to answer the demand aggregator can manage your demand. I think to promote this policy can help this to solve your question. I think that it may be not issue in this slide or ECAT policy, but ECAT only the demand response control center to look at that and control that. I'm not sure this is this can answer your question.
Yes, some have already been answered. The demand response management is one part. Another part also should be about the energy conservation, how to reduce the growth rate of energy demand to be slowed down. Because without the help of demand side management, peak load response and energy conservation as a whole, I think in this case, in order to achieve the objective that you mentioned, that will be very tough in my opinion for ECAT in order to achieve your very challenging objective. Because the energy conservation and demand response, that is the low-hanging fruit that we can make use of it easily when you compare, when you incorporate the renewable energy into the power development plan. This is my humble personal opinion. Anyway, thank you very much for your answer.
Thank you for the question.
โอเคค่ะ thank you very much again Dr. จำนงนะคะ so we have two more questions in the chat box. One is do you see major challenges in accommodating more future solar power projects which are not firm, using only 30+% of EGAT plants in the system? In other words, can you have control of IPPs to help you stabilize the grid system? How smart the grid needs to be and when to achieve this? Yeah, I think this has many questions in one post.
I think for the variable renewable energy is a challenge. It's really challenge for EGAT. Yes, and that that's it. Mean is the power grid flexibility and power grid infrastructure that we explained previously explained that power system flexibility equipment such as the STATCOM, VSC or battery. That is because in the PDP we have no exactly the location of the project, but we only know the capacity of the whole generation fuel. That means we can prepare only the grid infrastructure. That means the main trunk about the transmission system only. No flexibility equipment. If we have the exactly size of the project, that we will conduct the power system analysis to choose the suitable equipment, flexibility equipment to stabilize the VRE power plant. That means for the study, for the conducting the study, power system study, it should be have the accurate, such as the wind profile or the solar profile to the power system analysis, that you can use the suitable flexible equipment. It really challenge. I think that I can answer the question as this. Okay.
So the one who must be responsible for this is it EGAT or the company who sell the renewable power to EGAT?
I think before he proposed the project to EGAT, we should they choose propose the wind data, and technical data of the power plant to EGAT, and EGAT will conduct the power system analysis.
Yeah.
To be stabilized the fluctuation of the wind power, such as you would like to sell the 1,000 megawatt from the wind farm. That do mean you should, if you get the provide it to provide the wind profile data to get and the technology parameter of the machine to get for power system analysis. And the fluctuation to stabilize the fluctuation of the power. It will show will tell the investor to install more flexibility equipment to stabilize the fluctuation of the power. That you can to negotiate and to sign the PPA after. If you follow the EGAT study, that's the process of it.
Okay, thank you. Actually, there are a couple more questions, but I think within this remaining time before we move to the next presentation, there's one short question. Do you see potential of offshore wind for Thailand?
Yes, because the ADB has studied the ADB or DEDE have already conducted study of the offshore wind in Thailand and our Thai Gulf. It's about 700 megawatt near Ranong or Prachuap.
Okay, ครับ Okay, thank you very much คุณ again คุณกรเกียรตินะคะ So the remaining questions will postpone to the end of the presentations. Thank you very much. So now I would like to move to the next presentation. So we have heard from the generation and transmission authority. So we are now going to listen to the distribution network. And the next speaker is Mr. Ek Wattana Maha Subirachai. He is a Deputy Manager of Power System Analysis and Planning Divisions, Power System Planning Department of the Provincial Electricity Authority of Thailand. And today his presentation will be the PEA distribution network investment strategies, challenges and barriers. Mr. Ek Wattana, the next 30 minutes is yours.
Thank you. Good afternoon, everyone. Sorry that I close my camera because I'm not sure about the internet bandwidth at my office to make sure and avoid the loss of connection situation. So I please to allow me to close the camera. Okay, I will share the screen to present. Okay, I start from the PA overview. Our responsibility is the distribution system. We must distribute the electricity and the power to the overall of the country of Thailand, except in the metropolitan area, 3 provinces. So 74 from 77 provinces of Thailand supplied by PA. At the end of last year, we have the customer or meter nearby the 20 million customer. We have the substation is nearby the 700 substation, and the line length is maybe 800,000 circuit kilometer now that we respond and maintain it now. And the peak demand at the last year is about 22,700 megawatt at the last year. As you know, the COVID situation at the in the last 2 or 3 years make the demand is reduced, but at the last year the peak demand is the higher than COVID situation already for in the PA area. Okay. This is the overview of the PA distribution system. The main, we purchase the power from the EGAT to sell to the customer. In the yellow area, this is the trading point between EGAT and PA. It consists of the EGAT substation. We purchase the power from EGAT at the 2 voltage level. Mostly is the 115 kV, but in some area we still purchase at the 22 in overall area, but and the 33 kV at in the southern area of Thailand. However, in our 115 kV network, we have the small power producer connect at this level. The small power producer or SPP is the power plant that sell power is not between 10 megawatt to 90 megawatt. The power plant is both fuel power plant or combined cycle power plant and renewable energy power plant. However, this power plant is the contract with the EGAT. It's not contract with PEA, but the connection is the connect to the PEA grid. So this meter at the power plant site is linked to the EGAT metering. So this power plant is the same as the trading point between EGAT and PA2. And in the 115 kV network, we have the last customer, mostly is the last factory, or in some cases it's a big university, something like that, or sometimes is the airport in some province. And we purchase the 115 kV electricity from EGAT, and we have the substation that reduce the voltage level to the 22 or 33 kV. And same as the 115 kV network, the network is between each substation have the mostly is the open loop network, or have the tie open point between network at the 22 and 33 kV network level. In this network level, we have both customer and power plant is called the VSPP. VSPP is a contract directly with the PEA. VSPP is the very small power producer. Mostly is the renewable renewable energy, not supply the power not more than 10 megawatt contract. So, and at the present, the customer, especially big customer, they have the convert to the prosumer. Mostly of our customer, they install the solar rooftop at their site to reduce the energy cost and meet and make to follow to the carbon neutrality goal. And for the low voltage network, we don't have the, mostly we still supply with the radial system. It's not tie open point between another distribution transformer. And mostly is the customer in the household customer. But now many of households become to the prosumer. They install the solar roof at their roof in the house to reduce the cost, especially in this year. I think after this year, maybe we have this type of customer increase very much. So like the EGAT, PA must follow to the policy, upper level policy to support for the carbon neutrality. The vision of our organization is the smart energy for better life and sustainability. We try to upgrade our grid and upgrade our grid to modernized grid, upgrade to the smart grid, try to create some project to install the AMI meter, develop the microgrid area in some area, especially in this moment, we try to develop the microgrid project on the Iceland, in many Iceland in Thailand, and in the rural area that far away from main grid. Our strategic plan is that we have the strategic objective, have 4 strategic objectives. The first is the SO1 this is the make for the human resource upgrade and the change work process by using the digital and innovation to upgrade our work process. The SO2 is mostly the grid is in the SO2. We try to make the grid, maintain and upgrade the grid stronger and develop it to the smart grid in near future and in the long term for support the customer and stakeholder certification and support for the renewable energy connection to the grid in the future. The SO3 is try to create and leverage the new business to prepare for the changing of electricity market, because now Thailand is the electricity market structure is still the enhanced single buyer, but however in the upper level high policy, upper level policy, they have some policy to change this structure to the electricity market in the future. That means the traditional system, traditional process maybe can use in the future. We need to change our organization. And the SO4 is about the encourage and support all sector, including PA, to make the goal for support the carbon neutrality policy, such as the upgrade the power efficiency, encourage and support the using of renewable energy, especially the small customer like the household level or small business level. Okay, the PA is the state enterprise utility. We are under the government. We are under the government Ministry of Interior. When we make some project, we have the rather the long time project. From the previous slide, because our service area is very big. We have the large quantity of the customer. So when we create project for support for all, is the very big project because the implementation area is the all of country in the Thailand. So the feasibility study process is take time. It's about 6 to 9 months. And after that, we propose the project to the board of director, not more than 3 months. And after that, we propose the project to the Ministry of Interior. And after that, the project must be approved by the governments in the 5 section of the government. Is consist of the National Economic and Social Development Council, the Ministry of this organization will look for the overall of our project. And the second organization is the Ministry of Finance, and the third is the budget burial. The second and third is they consider about the finance and the budget that we use in the project. The fourth and the fifth organization is the Ministry of Energy and the Energy Regulatory Commission to consider about our project are followed by the energy policy or not. And every project of the PA, the investment cost is the effect to the energy tariff. So the Energy Regulatory Commission must be consider our project that the project suitable or not. This process is take the long time, maybe up to 8 months. And after that, the final process is about 2 or 3 months to consult of the minister. That means when we make decision to to make some project, we have the lead time at least 2 years before start to construction process. Take the wrong time. When we consider the project, study the project, we have the many input, but the mainly is start from the load or demand forecasting, like the PDP plan of that ECAT present previously. The second is the planning criteria. We have the planning criteria. I will explain in the next slide what it consists of in the planning criteria. The third is the unit cost. It means to evaluate the investment cost of the project. Suppose, for example, if we need to construct the new substation, how much of the cost of substation per one substation, or when we need to construct the transmission line, how much of the cost of transmission line per 1 kilometer. This is the unit cost to evaluate cost of the project. Next factor is the existing asset data. I mean, we need to know the existing data. How about the existing asset data can have some constraint or not? Suppose this substation can expand to install more equipment, something like that, or already full in substation. We need to know it, and in many cases we need to know about the condition and the age of the asset. It need to be the renovate or overhaul equipment or not, something like that. The next input data is the current and historical power quality data. Mostly is about the outage data, the frequency of the failure rate, how much often of when this equipment fail and make the outage to the customer, and the repair duration that affect to the reliability of the customer. And the next is the network model in the software. Today we PA use the power factory or disk silent to model the network and simulate the power flow, short circuit, and reliability, something like that. And the last is the other constraint. In some area we have some constraint or limitation from the regulation. In some area the local not allow us in construct the overhead line. If you need to expand the network, you must construct at the underground network, something like that, or in the some rural area, or in the Iceland, when we need to expand the network to this area, we need to have to the regulation to for PA make the environmental study, environmental effect study before start project, something like that with some area. And after that, we use this input data to design the scenario plan in the many options that can solve the problem. And after that, each scenario plan must be evaluate the economic and financial cost, what the scenario that more suitable and more suitable. We look after for the total cost. That means the includes for all both the installation costs, construction costs, operation and maintenance costs, fuel costs in some case, something like that. The total investment cost must be concerned. For the part of benefit, we mostly look about the electricity revenue, power saving, loss saving, something like that. And the last is the cost saving. Cost saving may be maybe sometimes is the cost of the customer. It's not the cost of PA. For example, is the outage cost when the outage occur in the system, the customer will shut down. What about the cost that they affect from the outage in the system? And after that, we select the best scenario to the PA project, and this project will propose to the follow the process as the previous slide. Okay. I go back to the planning criteria. Planning criteria, PA planning criteria is mostly consists of the loading and voltage constraint, sizing, quantity or type and property of equipment, substation or the network. For example, how much of the quantity of the transformer installed in each substation. The network in this area should be constructed using the radial system or loop system, something like that. The third is the configuration of the substation and network. The fourth is the conceptual design criteria. For example, in some area we can use the bare conductor, but in some area we can use the bare conductor. It should use the insulated conductor, something like that. Is the guideline for the design criteria. And the last is the area-based criteria planning. Area-based, yes, it means in planning criteria, we separate the area to 5 areas. It consists of the industrial area, the big city area, the general city area, the mini city area, and the rural or far away area. That means each area requires the reliability and security level is the different. That means the construction of the system and network is different in each area. This is the example of the planning criteria I show at the first topic, what loading and voltage constraint. For the voltage level constraint for easy conclusion, every voltage level except the low voltage network, the normal at the normal operation, the voltage range must be interval between the plus or minus 5% of the voltage level, and then and at the contingency operation condition, we allow it to more to the plus or minus 10% of normal voltage level for the every voltage level except low voltage. But for the low voltage is the same as the normal operation and contingency operation, plus or minus 10% is the follow to the IEC standard. And the second is because the distribution transformer, they don't have the auto load tap changer, so we can't change the tap at the distribution transformer, so the voltage level is the same as the two conditions. For the equipment is the similar as the voltage level. For the 115 kV line, we limit the line current load not more than 80% for the radial system, and loop line is the 50%. For the power transformer is the 75% of rated. This is the decision point that we make create the new project. Support the existing substation that install the one set of power transformer, support the 50 MVA. If the load reach 75% of 50 MVA, that means we need the project to expand for this substation, maybe install another set of the power transformer, or construct the new substation to receive some load from existing power transformer, something like that. We use this criteria to make our decision. Okay, I go to the case study that how PA take the feasibility study to expand the distribution system project. This case is in the Chiang Mai area. Prao district is the very small city in the Chiang Mai province. The population is not much, about 50,000 people in this city. But this city is located in the center, in the mountain. The mountain is around the city, and not only the mountain, it consists of the national park and the wildlife sanctuary are around the city. That means this area, if we need to expand the network, it need to the other constraint to the environmental study before create the new project. That means that take more time than 2 years to start the project. This is the limitation of this area. Okay, for the overview of the electricity system in this area, the supply power from the 3 substations each substation is one feeder. The mainly is the from the CDO substation in the purple color, about 40 kilometers. The second is the from the WPA substation in the orange color. And the last is the MRM substation is the green color. This substation is very long. To this area is about 80 kilometers. That means in this area it seems to be the load or demand is the located at the end of the line of all feeder. The problem of this area, okay, this is the load profile at the year 2021 in the 2021 from the CDO substation is the blue line is the about 5 megawatt peak. From the WPA is the about not much, about 2 megawatt, and from the MRM substation is the load is too high, about 8, nearly 9 megawatt. This is the load for all feeder. Is not only the in this city, but for the load in the only in this city is the yellow line is the nearly the load from the CDO substation is about the 4 to 5 megawatt peak. The peak duration on the night about 7 to 8 p.m. That means for this feeder from MRM, the load already over the capacity from planning criteria, because the planning criteria we limit load only the 50% of line rated, the about the 8 MVA. So this feeder is already over reached to the limit. This is the problem, the first problem of this area. The second problem is the very big problem of this area, because this area located in the center of the mountain and the forest. That means in the rainy season or the storm thunder, it have the outage from the tree, from the storm very often, more than 300 times in about 3 years. Outage occur in the over 300 times. That means if we say easily is the about every 2, 3 or 4 days have the one outage. Mostly outage time less than 1 hour per event, because it consists of the 3 feeder. For example, if the tree collapse and down to the purple network, that means the purple load will transfer to the orange and green feeder. So that's why the outage time is not take long time too much, more than 1 hour. But however, each feeder have the long distance to supply. That means when we transfer the another feeder to receive the power from another feeder, the voltage drop more than our standard. That means although the outage time less than 1 hour per event, but voltage quality is not in standard range. So the customer get the effect from this. So we need to solve this problem for this area by the 3 options. The first option is the traditional option, is the construct the new substation at the Prao district by construct new substation in this and construct the 115 kV transmission line along the same direction as the existing feeder. This can solve in the long-term problem. When it looks like we get the new source in the center of the city, it can solve problem on all. The second is also the traditional scenario for PEA planning. So because the load is not much, so the second is install the diesel generator connect to the 22 kV the feeder when the outage occur or on the peak duration. We start generator and supply the power.
Excuse me, Kun Ekwathana, sorry to interrupt you. Could you speed up a little bit because we are over the time.
Okay.
Thank you.
And the option 3 is like the previous option is install the battery storage connect to the 22 kV feeder because the peak duration is on the night only. So we charge the power at the before morning and discharge on the peak duration about 2 or 3 hours every day and can stand by for the outage event in the rainy season. This is the advantage and disadvantage of each scenario. The advantage of substation is the best reliability, best maximize loss saving, and can support in the long term is more than 20 years. But disadvantage is the highest investment cost. Take time to construct because the load, we construct the network along the load is on the mountain. The difficult than the construct in the general area. And as I mentioned at previous, more process from the environmental study. The diesel gen have the advantage, very low investment cost and very easy to install. But disadvantage is the pollution. Maybe pollution from sound and smoke have the problem with the social not good. High and uncertainty operating cost because the cost depend on the fuel price and they need to fuel stock management. For the battery system, easy to install as the diesel gen, no effect from pollution. In the future, it can upgrade system to the microgrid in this area because we already have the battery storage. So disadvantage is the new technology for the operator and maintenance guy. Cost between the diesel gen and substation. Can supply power all time, need energy management planning because the battery act like the load and source depend on your management. The cost for the cost is the same of it is the same cost of three options. It consists of installation cost, O&M cost, energy cost. But for the diesel generation, it have the cost from the fuel cost. For the benefit, we can get benefit from the incremental load saving, loss saving, and outage cost. This is for the economic only. I will explain later. Because as I mentioned previous, the PA is under government, so we need to evaluate both financial term and economic term. Financial term is the cost and benefit which directly affect to the organization. For example, in investment cost, every cost, electricity purchase and selling, this is the effect to the PA directly. For the economic, is from the financial and plus the cost and benefit that affect to the country and customer. For example, the investment cost, when we purchase the equipment, PA must pay some tax like the private sector. But when we evaluate the economic term, we minus this tax, we exclude this tax because the tax this go back to the country. That means investment cost in economic is lower than financial analysis. Another is the outage cost saving. This outage cost is occur to the customer. It's not occur to the PA. For example, if the factory shut down due to outage, they get some loss from anything when the outage occur. This is the result of financial and economic of each option. For option 1, the FIR is about 3%, EIR is about 8%. Option 2, diesel generator FIR is a minus. The economic is up nearly 7%. For the last option, battery, the FIR is the 4.7%, and the EIR is nearly the 20%. So in this area, we select the option 3 to install the battery energy storage system to solve the problem in this area. This is the way that's how PA work and create the project. Okay, that is all of my presentation. Thank you.
Thank you very much ค่ะคุณเอกวัฒนะ for your comprehensive presentation. As we are a little bit behind the schedule, but I think a short break is still necessary for everyone, like to just go to the restroom or something. May I propose to resume the session at 2:40? So we have around 6 minutes. So let's meet again at 2:40 for the other two presentations. Thank you. Hello. Okay, so it's now the time. So let's resume the sessions. Okay, so far we have heard about this, the status and the plan for Thailand. So now next, we move to hear about the international experience from data tech experts. And the first is Mr. Victor Bedoya Restrepo. Okay, from data tech, and the topic of his talk is unseen impacts of renewable energy integration and grid infrastructure interventions. Okay, Mr. Victor, the next 30 minutes is yours.
Okay, thank you so much. Can you hear me?
Yes, very clear.
Yeah,
Thank you.
okay. Just give me 2 seconds. I'm going to share my screen. Can you see my screen?
Yes. Yes.
Okay, perfect.
Perfect.
Okay, now thank you so much for the invitation to this webinar. I'm Victor Bedoya. I'm electrical engineer. Most of my background or my experience has been in the operation of power systems. And also in the last 4 years, I've been working on different projects as a consultant. I have had the opportunity to work in almost 10 countries around the world. So I want to share here some of the experiences that I have had in those countries with those projects. I want to share with you the knowledge that I have in this part, which is part of my passions, which is integrate the renewable energy to the power systems. So the idea here is basically we are going to talk about the integration of renewable energy in power systems, but at the same time, I want to highlight some aspects that sometimes we don't consider in the first stage when we are talking about renewables. Sometimes we start thinking about renewables like something that is going to be new for the grid, that it's going to bring a lot of benefits, a lot of improvements to the energy sector. But if we don't have that kind of exhaustive energy planning, this could be also a very big challenge in the future for the power system. So the idea here is that we have two perspectives of the integration of renewables in the power system. Then the first side, or the first perspective, will be the good things that we can have with the renewables, but also we want to see another perspective with the different challenges that we have seen in different projects around the world and different experiences with other countries. So that's the idea with this webinar. So let's proceed. Then with the unseen impact that we can have with the RE integration, we can also see that once we start evaluating those impacts in the network, we are going to come up with some solutions, right? So these kind of solutions are part of those plans that we have to solve all those challenges that we are going to have with the RE integration. So in this case, as I mentioned before, we are going to have a positive impact, let's say, in this positive impact, I think the major positive impact that we are going to consider here is the reduction of greenhouse gas emissions. That basically is to reduce the CO2 emissions. This is something that is aligned with all countries around the world, at least all countries that are part of the United Nations. They have that kind of climate goals, and this is a priority right now. I mean, global warming is a challenge right now for humanity. And in the power sector, we have this challenge right now. So the renewables, when we are talking about the wind projects or the solar projects, uh, we also think that these are green technologies, and then the reduction of the CO2 emissions is very effective. So for this kind of aspect, I can say that this is the more, or this is the greater impact, positive impact that we have from renewables. But we also have then that we can improve the grid reliability. We can have a very good amount of energy that it's going to be connected or integrated into the system, so we can get benefit from that kind of renewable integration. Also, increase the energy security. In some cases, when we integrate the renewable energy, we also are going to invest in the power network. So the idea is that everything that we are going to use as a complement for this renewable integration is going to improve, or is going to increase the energy security in the power grid. So this is something that we also have as a positive impact. In the social aspects, because we are having this boom right now with the integration of renewables, of course, we are also impacting the communities, and we are also impacting the job creation in countries. So this is also a positive impact that we have with the renewables. And reduced energy cost. As you may know, we have been using the fossil fuels for energy production for a lot of time. We know that that kind of energy is quite expensive. And if we compare with the renewables, basically the primary resource, like the wind and the solar irradiance, is for free, right? So this is going to lead that basically we are going to reduce the energy cost, and at the same time the materials that we are using for creating the solar panels and also the wind turbines are decreasing very fast. So this is also helping the integration of renewables into power systems. Then let's talk about the other perspective, that in this case are the challenges that we can also see with this renewable integration, right? So the first thing that I want to highlight here is the power system flexibility. With the power system flexibility is basically the system should be prepared to absorb the variability that we are going to have with the renewable energy, with this integration. As you may know, we have a lot of variation due to the different changes that we are going to have in the wind speed and also with the solar irradiance. Then the system should be flexible enough to absorb that kind of variations. If the system is not flexible enough, it means that you have to create, let's say, a market mechanism or a different, or you have to have a different strategy, right, to have that kind of flexibility and integrate the renewables in your system. So it's going to be like a balance. you are going to integrate the renewables, okay, you have to think also if the system is flexible enough for that kind of integration that you are thinking or that you are planning in your system. The second one, challenge is it's going to be the grid stability. Basically, these kind of technologies, in some cases, let's say for the solar generation, for the solar PV, we are going to use a lot of inverters. So this is quite new if we think that we are going to use this in a massive way. So let's have another perspective that what's going to be the impact that we are going to have in the grid flexibility for all these new technology that we are incorporating into the network. So that will be the second bullet that I want to highlight here. Another thing is, in most of the countries, we are seeing that there is a fast growing of DRE connection or the integration of small scale projects into the network. And in some countries, there's not regulation to integrate these kind of small generators into the network. The idea here is think on regulation, right? That will be another critical aspect that we have for this renewable integration. So what I want to highlight here is in most of the countries, of most of the power system, they are, let's say, focused on the big amounts or in the largest generation. In this case, for solar panels or for wind farms, but in the case that we're talking about small scale project, we don't have that kind of regulation. We don't have that kind of interest at the moment, and this is growing very fast. So somehow we need to continue improving the regulation for the larger generators, for those generators that in most of the country we consider that are larger than 20 megawatts. But at the same time, we need to start thinking in how is going to be control the integration of those distributed energy resources that are going to be in the network as small generators, right? So that's something that we need to talk here. That's going to be about regulation, okay? Another aspect that we can consider as a challenge will be the land use and the conflict that we can have when we are talking about those large projects, when we are talking about large integrations of wind power plant or solar power plant. We know that most of these projects require a huge amount of land. So in some cases, we have seen that in countries we are having some issues with the land use. So at the end could be also a conflict. So this is something that we need to highlight and think about it when we are talking about RE integration. Also, the social impact, how you're going to involve the local communities, how you're going to work together with the private companies, with the private investors, and also with the universities, and also with the different ethnical groups that you're going to have around the project or around this integration. That's something that we want to also highlight here. It's like how to integrate local communities, universities, private investors, all of them working for the same purpose, that would be an organized, well-prepared RE integration in a power system. And something that is quite new, that maybe can also have a lot of opportunities, new opportunities. We need also a lot of research in this topic, will be the material disposal. As you may know, let's say the first fleet of this renewable energy integration was connected, let's say, between 25 and 30 years ago. Some of them are going to decommissioning, and then we have a new challenge right now that will be how it's going to be that process for material disposal. Okay, and this is going to be also an opportunity for different countries, and on start thinking about it and try to lead this challenge and try to create initiatives that are going to help the world and are going to help the RE integration in different countries around the world. Okay, let's talk about the power system flexibility. This time I want to share with you one of the examples, excuse me, that we have in Kaizo. What I brought this example here, it's basically because in Kaizo, we have, Kaizo is the ISO in California, in the US, is the independent system operator there. And basically they have a structure that it's going to be electricity market dependent. Basically, everything is integrated into the system based on competition between different technologies. And then with this kind of, let's say, structures in a power system, this is the trend that we are seeing for the operation of a power system. Then I want to highlight here that you can see here what's the amount of renewables that they are having right now in the network. You can also compare here that if we talk about the current demand, that could be around 22 gigs, 18 gigs are coming, or in some periods can be met by the renewables. So look at this strong trend that we are having in the power system, and with the integration of RE in this kind of markets, in this kind of systems, and then how they are dealing. If we use this as an example that we can have in our country, just to see what will be the future that maybe we could have in our system, then how they are dealing with these kind of different requirements that you have for that RE integration. Then in this case, they are also dealing with, for example, the decommissioning of coal power plants. Basically, coal, it's very unusual that we already have like private investment on coal due to the different issues that we are having with climate change. We know that due to the COVID-19 and all those problems that we had with the different integration of generation around the world due to the COVID-19, then this came up again with some let's say integration or use of the coal as a source of generation. But we think that this is going to be for a short period, and at the end of the day, the coal, it's going to decrease every time his share in the power system as a source of energy generation. So these kind of technologies, you can see that the share to meet the demand is very low. Example was the coal, and also we can also see here that they have integration of batteries. So batteries are coming as a solution basically for this kind of RE integration. Then with the batteries, they are also trying to improve the reliability of the system and basically the flexibility of the system for these different ramps that they are going to experience or that they are experiencing in the system due to of course the variability and also the nature itself of the renewable generation. Then these kind of aspects are very relevant, very important for the flexibility, what it's around of this integration, what other technologies are they incorporating to improve the flexibility. In this case, the batteries is something that they are incorporating into the system to lead with, to deal with this specific issue. Also, the imports or the interconnections with other systems, with the central power system in the US, it's also helping this kind of increasing flexibility in the system. So this will be also another aspect that we want to highlight here, that another source of flexibility can be the integration with other systems, can be that kind of import export that we are going to have with different areas and also with another countries. So this could be also an aspect that we want to highlight here. And another one, of course, that it's going to help on the power system flexibility, it's going to be incorporating complementary technologies that are going to help on those fast ramps that we are going to have in the system. In this case, they are also working with these natural gas engines, where basically they are taking advantage of these technologies and the fast response that they have in a power system to basically provide that kind of flexibility that is needed to incorporate the RE in the system. So that's basically the different technologies that they are using right now to incorporate flexibility in the system. Other technologies which are basically quite, let's say, rigid, could be, for example, the nuclear generation, that we know that the flexibility of these power plants is not, is still, let's say, under development. We are still, or the engineering is still working to try to improve the flexibility or the speed of the different ramps that we can have with the nuclear generation. But at the moment, nuclear generation is a very effective generation to be on the load base, but to supply that kind of challenges or to provide a, let's say, effective solution with these kind of challenges with flexibilities, they are still on the process. So this is basically the big picture that we are going to have in most of the power systems in the future. And yeah, that was the thing that I want to highlight here with this slide. So let's go to the grid stability. and how we can incorporate new technologies into the system that are going to work as a complement for this RE integration. Then for this RE integration, then we are going to have basically different challenges on network congestion, voltage stability, frequency stability, and transient stability. In this case, there's something that came up in different power systems that it's basically to solve part of these problems. They are using new technologies, and these new technologies are based on this kind of equipment that that are considering inverters or this electronic power that we can incorporate into the power systems, and it can solve specific problems, and in sometimes it can help you to avoid the network expansion. Then I'm talking here with the flexible IC transmission system that could be, for example, for the STATCOMs, that basically you can provide different requirements of reactive power into the network. So in some aspects, you can, let's say, help in specific situations, for specific contingencies, you can support the operation of the system, and then in this way, you can also replace the network expansion with these kind of new technologies. We can also see that the batteries for network congestion could be also a very good solution. So basically, the batteries can be charged during periods of low load, but and they can discharge or provide the energy during the peak load. So that will help us with the network congestion and also to solve the thermal limits. For the frequency stability, as I mentioned before, we are also incorporating a lot of inverters into the network. One of the challenges in some of the systems that we are having is basically when you integrate a lot of generation like PV solar panels into the system with inverters, because you don't have rotating machines for these generators, then you are losing inertia in these kind of systems. So this is something that we need to also discuss when we are talking about our integration, if we will need different synchronized compensators into the network to provide that kind of inertia that is needed in the system. And for the transient stability, whatever is needed to adjust the different technologies that we have for the power system stabilizers, and also for the automatic voltage regulators, and basically to improve the energy security in the system, and avoid that when we are having a large integration and different, let's say, interconnection with larger systems, that we don't have any kind of issues, let's say, with power system oscillations and that kind of stuff. So these are different technologies that are also impacting the RE integration into the network, and also improving the different situations that we are having with the RE integration. Then also, I want to talk here about the regulation. It's something that we need to highlight here. I have basically 2 points that I want to highlight here. The first point, it's going to be all these small generators that we are connecting maybe in a non-controlled way into the network, that basically they are behind the meter in some of the houses, in some of the small business that we have in the cities, and if we don't have a regulation that it's going to control the growing or the conditions and how these generators are going to be installed into the network, this is going to be a problem that the utilities are going to experience in the system. So this is something that I want to highlight here, that this is going to be a work that it's going to be with the utilities, it's going to involve the utilities and also the regulators in the country. And also the different requirements that are needed for the integration of REs. So it depends of the amount of the installed capacity that you're going to have with these RE integrations. What are going to be the conditions that you are going to have for the secure operation of all those generators? Then in this case, we want to highlight here the different conditions that you are going to have to keep the stability in voltage and also to keep the stability in frequency. And in another way, other complementary, let's say, functionalities that are around this RE integration are basically, let's talk about how it's going to be the RE, the reactive power, the reactive power generation, what's going to be the way to compensate the reactive power in the system, different things like the forecasting, how the generators are going to provide that forecasting to the network or to the system operator, and also what's going to be the strategy, who is going to provide the forecast. The forecast is going to be provided in a centralized way, or is going to be provided in a decentralized way. What are going to be the conditions that we are going to have from different projects to provide that forecast, and that information, it's going to, of course, improve the reliability and of the operation of the power systems. Also, the different conditions that we are going to have for control and supervision of the different REs that are going to be integrated in the system, and the testing process. With the land use and conflict that I mentioned before, basically in some countries, I'm talking about some in North America. I know that in Canada, they are working this kind of projects, but also in Germany, France, Sweden, Japan, they are also thinking in how to change a little bit the way that we are expanding the solar generation in the world. As you may know, this is taking a lot of amount of land, the expansion of this technology. So we are having here new developments that are now, let's say, in a testing mode, and basically is how we can save that space that is needed right now for this solar generation. So they are thinking on let's say vertical configuration of the solar panels. There are some challenges that they have to deal, or some challenges that we are going to have here with this technology due to the angles that we are going to have from the solar irradiance, what's going to be the efficiency that we are going to have with this kind of configuration. But my point here is I want that you also see that if some of the countries around the world are working on this, is because these will be part of the future, and these will be also a very good idea that you can have for the integration of universities and private investors and how you can solve these kind of problems. Then this will be something that you can see as an opportunity for research, and how you can also be part of these solutions that the world are creating for these kind of problems in RE integration. Another thing was
I'm sorry, Mr.
yes.
Victor. We are already behind the schedule. Could you speed up and finish maybe within 1 or 2 minutes? Thank you.
Yes. Okay, thanks. Okay, and then with the social impact challenges, I want to show you here some experiences that we had in a project in Latin America. That basically, these are the types of problems that you can have when you are creating a wind farm project, a large wind farm project. So in that case, we experience these kind of challenges with the landscape and visual impact, also with the property values. We need to work with the community, basically to engage this community and let them know what are the different advantages that we are going to have for the integration of renewable energy. But also we have to be honest about the different challenges that we are going to have, and talk about the different compensation that the local communities are going to have for the integration of the renewable energy. If you don't have that kind of strategy with local communities, the RE integration is going to be very, very difficult. If you have that kind of opposition from local communities, that's not good for the project. So in these countries, we also had some support from USAID to work with the local communities and engage them to the different projects. So at the end of the day, they can be part of this project. They can feel that the project is part of their communities, and also they are going to have benefits, different benefits from this kind of projects. So at the end of the day, they are going to support the integration of RE. So social impact, very important, the work that you are going to do with the local communities and how to engage the local communities. And this is my last slide. And basically, when we are talking about RE integration and the challenge that we are going to have with the decommissioning, I just want to leave here this example that basically most of the countries are start thinking about how to leave this kind of disposal of material. So in France, we already have one of the, let's say, recycling plants that are going to be focused on the decommissioning of these photovoltaic panels, and basically the recycling process that we are going to have with this kind of material. I'm not saying that this is the only example around the world. We also have a lot of examples, but this is something new. So this is going to be an opportunity that we are going to have because this boom that we are going to have with the, or that we are having with the integration of renewables, at some point we are going, or we have to deal, and we have to be prepared also for the decommissioning of those power plants, and also let's say the connection of new technologies in the system. So that was all from my side. Sorry for taking a few more minutes, but I hope you enjoy the presentation, and I'll be here if you have any questions. Over to
Okay,
you.
thank you very much, Mr. Victor, for the comprehensive information. Yes, so now I would like to move to the last presentation for today. The last presentation for today is on the topic international experience on energy system least cost investment optimization strategies for power system expansion, best practices, lesson learned, and challenges. And we have dual speakers, Mr. Paul Tucson and Mr. Tristan Kusis. So both are from Data Tech. Okay, so now the next 30 minutes is yours.
Good morning, ladies and gentlemen, and distinguished guests. Myself and my colleague Tristan Cases will be presenting these slides. It is our pleasure to speak to you today on energy optimization, modeling, and investment strategies for generation, transmission, and distribution. Thank you. Next slide. We hope to bring to the discussion our international experience on energy system least cost investment optimization, and we touch on best practices, lessons learned, and challenges. Next slide. Next slide. In terms of international best practices, the European Union established the European Network of Transmission System Operators, ENTSO-E, the European Network of Transmission System Operators for Gas, ENTSO-E-G, and provided legal mandates to manage the internal energy market in Europe. The aim is to liberalize the gas and electricity markets in the EU and provide a pan-European transmission system. The main objectives are to integrate renewable energy resources into the energy system, ensure affordability, sustainability, and security, stimulate cross-border trade, and ensure efficient management and coordinated operation of the EU gas market. Next slide, please. ENTSO's 2020 goals are to increase the share of renewable energy to 20%, reduce the greenhouse gases by 20%, and increase energy efficiency by 20%. 2030 goals are to achieve 55% reduction in greenhouse gases. 2050 goals are to achieve full decarbonization. For this to succeed, this requires voluntary cooperation of member countries from a policy standpoint. Next slide, please. Next slide. So there are many global energy system events that we can learn from. Just a few are listed below. The Texas extreme weather and load shedding event. This brings to mind climate resilience. The UK load shedding event, increased renewable generation and insufficient ancillary services. South African load shedding, aging thermal generation fleet, and a slow rollout of renewable energy generation, storage, and transmission infrastructure. Central Asia hydro generation risk from changing hydrology and glacial water flows. The Fukushima nuclear generation incident, climate resilience again. Barbados fault level reduction projection based on the planned increase of renewable energy generation up to 100% renewable generation by 2035 and 50% by 2030. And the California load shedding event, which highlighted insufficient capacity and the need for a capacity market. Next slide, please. So planning has to evolve from a reliability, least cost, and deterministic model to the right-hand side of the picture to a resilience, least regret, or best cost and probabilistic planning model. Resilience planning is the ability to withstand disruptive events, and best cost planning considers climate, environmental, resilience, and other costs. Next slide, please. Historically, electricity demand was predictable. Thermal and hydro generation technologies were dispatchable, and they met the demand, and new generation was introduced to replace retired generation. Today, energy substitution to electricity is increasing. Example, electric vehicles and electrical cooking. Thermal fossil fuel generation harms the environment and is often inflexible to cope with modern systems and renewable energy. Old coal stations and old steam gas stations are very inflexible. Aging and retiring thermal generation requires replacement with new generation and with variable renewable generation and energy storage systems. And the grid needs to adapt to satisfy this changing energy landscape. Next slide, please. The challenges of modern power systems include legacy and aging generation, intermittency from renewables, reduced inertia from inverter-based generation, decreased fault levels from inverter-based generation, and the mitigation to decreased fault levels are synchronous condensers, which not only provide inertia and dynamic voltage response, but also provide the fault level. Seasonality, storage to compensate for renewable energy patterns, way leaves and capital for new transmission lines and transmission systems, extreme weather events. Load duration curves and average load and average generation are no longer sufficient. Hourly stochastic analysis these days is required for effective planning and operation of a power system. Next slide, please. So modeling today is required over many weather years, and modeling must be chronological. That means hour by hour, not just average values, and not just hour by hour for the year, but hour by hour for future years as well. And times of peak, renewable generation and storage, charging and discharging don't coincide, and they all need to be understood and managed and modeled correctly. Next slide, please. So as I'm sure you are all well aware of, Thailand is part of the Greater Mekong and the ASEAN countries. Similar to ENSO, it is an interconnected system. Next slide, please. So Mekong and ASEAN countries are on an energy transition pathway, just like the rest of the world. All these countries are experiencing the effects of climate change. Benefits from regional integration include the following: weather diversity and resilience. What does that mean? Well, it means if the sun is shining here, not shining here, it might be shining here. If the wind is not blowing here, it might be blowing here. So if you've got an interconnected system, you are getting a reserve and you are getting diversity in generation. And resilience, if there's a very bad storm in this part of the country, the other part of the country is not experiencing the storm. Or if this country has a bad weather event, the other does not. And as an interconnected system, the countries can help each other and the regions can help each other. And if countries are interconnected, there's a reduced requirement for reserve. Instead of the reserve being an arithmetic sum, all the reserves are pooled and there's a probabilistic sum that is much reduced. overall, it'll lower the cost of electricity because it's just the cost of transmission interconnectors rather than have each country having to build its own autonomous generation. Interconnected countries can incorporate more renewable generation, and new transmission requirements and ancillary services requirements are going to need to be relooked at as the renewable generation increases. Next slide, please. And I will thank you for your attention, and I will now hand over to my colleague, Tristan Cases. Thank you very much.
Thanks, Paul. So I think within the past few sessions, we've discussed some of the challenges, some of the new technologies that we're seeing being introduced into the power system from a generation standpoint from EGAT, and then looking at the different distribution networks in Thailand as well, and some of the challenges around that, particularly in areas where there's potential high amount of environmental sensitivity. Now, then we went on to Victor, who spoke about some of the challenges and how to deal with these, some of the technologies to overcome some of the challenges with increased RE. Now, what we do still need to understand is that as engineers, as planners, we are going through this energy transition where historically it was a lot simpler to do this planning. Understanding that you have a certain electrical demand and you need to meet this electrical demand with some new generation candidate. As Paul mentioned, historically it was a lot simpler to do that because you had firm dispatchable generation that used fossil fuel power plants. But now we're moving to a space where we have to look at all of these other constraints in the system. So as a planner, we need to understand these long-term energy systems requirements. And fortunately, there are tools to help us out with this. There are a range of tools available that, for the most part, are only commercially available and very expensive. But they have assisted planners and engineers on this process of designing the future energy system. And over the past few months, Paul, myself, Victor, and a couple of other colleagues have been working closely with KMUTT to introduce a new tool called PIPESA, Python for Power Systems Analysis. And what are we doing here? We're using this tool to optimize social welfare for a country, for a region. So next slide, please. So what is this tool? Python for Power Systems Analysis is a free software toolbox for simulating and optimizing modern electrical power systems over multiple periods. So some of the topics that we've discussed today, PIPESA is a really useful tool for helping us understand the system, helping us design it, looking at what are the potential decisions that we can make. And with this tool being free and open source, it means that you don't need to be a government utility to use it. You can be a researcher from a university. You can be starting up your own business and looking to understand a power system and provide support to governments. So what else do we know about PIPESA? So PIPESA includes models for conventional generators with unit commitment, variable renewable generation, storage units coupling to other energy sectors, and mixed alternating and direct current networks. So on the bottom left there, you can see an example power system that looks not only at your electrical network, not only at your electrical generators and your electrical demand, but also at other sectors in a country. So what about if you need to understand the heat energy required during cold periods in the year? Some countries have historically made use of combined heat and power plants to provide power to towns while leveraging the excess heat energy from these thermal power plants. On top of this, pipes is very useful for looking at other parts of the other sectors, potentially looking at transport as well, which, as we have discussed today, is something that's going to become more and more important, looking at the introduction of more EVs on your system. Next slide, please. So pipes are developed by a number of universities and researchers from around the world. Has grown, and there's a large user base. We are currently using it, and we've been working with KMU-TT to use this as part of the project's evaluation. And this is one of the tools that we see that's going to assist in this energy transition and helping planners and governments and countries move forward along this process. So the next few slides that I have over here, I'm not going to go through because I know we are now a little bit over time. But please take the time to go through this, to have a look at some of the capabilities of PIPESA, what you can do with it. It's not only looking at planning a whole from a country point of view. Sometimes it's looking at assessing the cost benefit analysis of a rooftop solar in your own house. What size batteries do you need? How many panels do you need? And this is where we think it's a perfect tool for many people to start using in this space. Next slide, please. Yeah, so just having a look at some of the other existing tools in the space, you can get an idea of where PIPESA fits in, having the unique space of allowing you to look at the power system from running load flows, and then also on the other end, looking at the economic side of things and investment optimization. All right, so I think you can go to the last slide of our session over here. So yeah, so this is just a look at why we believe PIPESA is so useful. As I mentioned earlier, it's free and open source. And the benefits of this is that historically, these tools have been closed. You had to pay for them. A lot of the analysis and the data that went into these processes was not known to many people. But now we are seeing this change where with these new tools, we're looking at open data, open source tools to actually conduct these optimization problems. And then right at the other end is also providing open data for the results. So everyone from engineers, scientists, modelers, and policymakers can understand and have their say in the process of this planning, which ultimately assists in the end goal of providing optimizing social welfare. Thank you.
Okay, thank you very much, Tristan, and also Paul just now. Okay, so now we are in the session for the question and answers. If anyone has the question, you may raise your hand, and I will invite you to ask the question. And I think for the previous questions, like the one to EGAT, I think Kun Konkiet already answered. One is on the EV, the increase in the usage of EV, and okay, so let me read a little bit, just in case for those who are on the Facebook Live, don't know. So the question is, sorry. With the electric vehicle to be incorporated by the government of Thailand by 2030, there will be an increased demand for electricity, and we may see peak demand during the night time when people would be charging their EVs. What plan does ECAT have in order to meet this major challenge? Will ECAT have to revert to increase share of fossil-based production in order to meet this demand? And the answer to meet the peak electricity demand at night, ECAT plans to use battery energy storage, hydro pump storage, other renewable energy such as biomass, biogas. Some fossil fuels will be used for electricity generation when the renewable energy is insufficient to generate electricity. Okay, I can see two people raise the hand. First is Dr. Jamnong and followed by Dr. Bandit. Dr. Jamnong, please.
Yes, thank you very much. I have one question for Mr. Kusis about your Python's modeling tools. My question is that your objective function, this is a single objective function or it is a multiple objective function? That's my question. Thank you.
Yeah, so the way PIPESA works is it conducts a linear optimization, and as you say, it's formed by putting together a linear optimization equation, but now that linear equation that's put together is highly dependent on the inputs that you provided. So just as we heard in the feasibility study of the distribution planning case study, there were a number of parameters that were provided and given to and fed into the problem to say these are constraints on grid voltage levels, these are constraints on the magnitude of load that you can expect to run through a certain line, these are the expected demands that we're going to see over time. And it's a similar situation in PIPESA. So you would give it all of those parameters, and that linear optimization, that equation would be adjusted to satisfy the what you've provided it with. So you're going to provide it with a demand, constraints on potentially the timing of that demand, generation candidates, how those generation candidates function, how much they cost, when they go into and out of service.
Yes,
so
yes.
it's really dependent on how much information you provided.
Yes, but that is not my question. My question is that your output is the objective the answer of objective function, isn't it? If it's yes, then my question is that the output, the objective function, is a single objective function, or the answer is multiple objective functions?
It's so currently how it works is that yes, it's a single objective function, gives you a single objective value. So it'll provide you with the least cost version of your system. However, there has been work from the folk at PIPESA to look at something they called modeling to generate alternatives. So sometimes there is a local optimum or a global optimum to say this is the best system that you can build with your input criteria, but you can also look out at potential other options that may be not the most optimal, but may also be feasible candidates. So maybe you don't build this much solar PV, but you can also look at introducing a different transmission link, which is a different alternative.
Okay, thank you very much.
Okay, Dr. Bandit.
Yes, thank you. I have two questions. The first one is maybe to Paul. the previous speaker. You mentioned the challenges of energy system planning. The one that you mentioned is land use. To address land use change, land use conflicts with renewables. One solution is to use a vertical configuration solar PV, for instance. That is rather extreme. What do you think of the agri-PV, agrovoltaics, so-called? That is the use of one piece of land for the co-production of energy and agriculture. Do you see that as a solution?
I think that one was for me. Yeah. So yeah, thank you so much for this question. And yeah, this is an issue that we are having right now with the expansion of renewable energy. That basically the amount of land that is needed for these kind of technologies. And when we talk about these kind of technologies, we are saying that we also need a good amount of land for solar PV technologies, and it's going to be also, I mean, a good amount of land for the wind farms, right? So the idea here is how to deal with that requirement of land. Then from an engineering perspective, the engineers are working to try to save land, to try to save space, right? And then this solution that they are trying to develop right now is basically they want to reduce the space that is needed for the solar PV projects, and use this kind of a configuration, which is vertical, and you can see basically that you can save a lot of space, right? What's the idea with this? This is part of a plan, because the issue with the land is you are going to have a conflict, a competition with other type of uses. In this case, also with the agriculture, let's say. In some cases, you can say that you can have a very good, let's say, combination between renewable energy and agriculture in this kind of configuration. For example, for a wind farm, you can say like, okay, for these kind of projects, the agriculture is still something that we can do in this land that we are using for the wind farm project, right? That will be something that I think is going to work, that we can see that is implemented in different countries. But when we have conflict with other type of uses, let's say with urban areas, maybe when you see what's going to be the relationship that in the urban areas are going to have with this kind of wind farm projects, there's going to be a conflict, because in some cases people don't want to see or don't want to have that kind of projects around their houses. And in some cases we have seen in Europe and in the US that these kind of projects are also impacting the value of the properties that are around or that are surrounding those projects. So it depends of the different, let's say, actors that we are going to have for these configurations. Then for some actors like the agriculture, it could work if you don't see any issues, right, between this combination the renewable energy plus the agriculture, but with other type of actors like the urban areas, you can see that you're going to have some difficulties to lead with this kind of land conflict. Then, yeah, these are two aspects that are part of the work that you have to do with the local communities. And also when you are going to plan this kind of renewable expansion in the country, what's going to be the use that you're going to have for the land for specific areas when you have identified that the primary resource is very good.
Thank you. Yes, I have another question. I'm not sure who to address, but the question is about human resources needs and workforce development. You see, the challenges of solving the power system problem is so immediate. A while ago, we were thinking to address the integration of valuable renewables into the grid. It's a big problem, but now the climate resilience comes into play. So I wonder, with the developing countries in particular, we would have a huge challenge in the human resources that we have to solve these problems. I wonder what are your ideas in resolving this, how to address the problem of workforce development for this particular sector.
If maybe I can start. I want to say that in some of the experiences that we have in different countries, the best way to start with the integration of renewable energy is start with this kind of trainings and work with the different communities that are interested in this kind of projects. So I want to say that it's very important that, for example, in Thailand, that you have, let's say, this work together. I mean, the university with the private companies, the university plus the power system operator, the university plus the regulator, the university plus the energy entity who is in charge of the planning of the power system. So this is going to be a very important aspect. And the way to do it is the university should be open to work in this kind of research that are now the focus of the private investors, right? And then the university should be that partner that should work together with all these energy entities plus the private sector to have development and somehow satisfy all the requirements that are needed for the human resources that are going to work on the energy sector. So I think the best way to do it is with this kind of trainings, involve the universities in the country, and then try to work together, try to involve the university, always working with the different energy entities that you are going to have in the country.
Thank you.
Paul, would you like to add something? Could you are unmute.
Give just a very personal experience. I've got a 6 kilowatts of PV on my roof. I've got a 10 kilowatt inverter, and I've got 20 kilowatt hours of batteries at my house. And I installed it myself. And I'm not a renewable expert. I'm not an inverter expert. I'm not a battery expert, but I installed it myself. So the barrier to entry is not high with renewable. I know that's not utility scale, but I'm just trying to give you some indication. When it gets to utility scale, the contractors know more about the PV plants, the PV panels, the inverters, and the wind turbines. They know more about it than we do. They supply it and they install it. So countries always tend to be cautious, always tend to be nervous about implementing these new technologies. But fortunately, this has not been done. This is not the first time this is being done. This has been happening in every single country in the world for the last 20 years. Contractors up to speed. Everybody, suppliers are up to speed. They know exactly what you need. If you say you need a 20 megawatt PV there, they will design it. They'll use PV systems, they'll use helioscope, they'll look at the land, they'll look at the geotech issues, they'll look at the environment, they'll get environmental guys involved, they'll look at the transmission integration, they'll hire consultants like Tetra Tech to do the integration studies, or your own engineers to do the integration studies. Consultants can assist your utility engineers with those studies. It is not a huge mountain, it's not a technical mountain, it is actually very achievable. And the trick is just to take the step, just to take the first step and just start doing it. And that's my answer. Thank you.
Okay, so thank you. We have time for another question. Dr. Natapong, you be the last person to ask before we close the session.
Yeah, thank you. I have a short question for Treason regarding the PISA. It's a Python for power system analysis. Could you please explain briefly the capability of the PISA compare with the commercial power system software like Dixilent or PowerMet, and also for the energy modeling like for the Markel or Leap model? Can you please show the advantage or disadvantage for the PISA compare among them? Thank you.
Sure. So I think maybe this is best illustrated by this slide. Just let me know when you're seeing it. It's called, you'll see these two circles over here, this Venn diagram. So I think this illustrates quite well the difference in the different tools available currently, and where the different tools fit in to this power systems planning space. So what you did mention about Dixilent and the other tools like Times and Markel is very interesting, because PIPSA sits in between these two types of tools. On the one side, you've got PSSE, Dixilent, ETAP, and those are your conventional power systems planning tools that you would look at from the perspective of running a load flow, running a short circuit, looking at your stability of your system. And then on the other end, we've got the tools like Plexos, Times, Markel, and those are more on the economic assessment, looking at the energy system, understanding investment optimization and dispatch of plants. And those tools, historically, these tools don't overlap much in their features. So the power system planning tools don't really have an understanding of the economics. And on the other side, the economic system tools often use simplifications for modeling the power system. So either by running a DC load flow, you lose some of the detail that you would have in your in tools like Dixilent, but then you are then very focused on looking at the economic side. So PIPES, as you can see on this figure over here, sits in between a lot of these tools. It doesn't have functionality that it doesn't have all of the functionality of all of the tools that you see here, but it's a hybrid between a lot of them. So for example, you can run a power flow, you can run a linear, non-linear power flow of your system. There are plans to introduce short circuit analysis into the tool. And on the other side, it also has the ability to model the economic analysis from a linear optimal power flow to security constrained linear optimization, multi-investment optimization, which we are quite focused on at the moment with the course with KMUTT. And then also it's very useful as you can model other energy sectors. Just having a look at some of the other tools, yes, a lot of these other tools are paid for. There are other free and open source variants that are out there. So as an engineer, as a researcher, planner, you can choose which tool suits you best. And that's looking from potentially you might go with the likes of Plexus because they offer support, or you might go with something like Pipesa or Calliope or Osmosis, and these are free and open source tools with different feature sets. So it's very dependent on what you are looking to accomplish in your work. I hope that answers the question.
Okay. Okay, thank you, Tristan. So I think that is the end of the webinar today. So I would like to thank you once again for all the speakers for the insightful information and valuable experiences that you share with us. Also, thanks for all the participants for attending this webinar. So I hope you enjoyed the webinar and found it useful. Your feedback will be valuable in helping us improve the future events. So please complete the questionnaire by scanning the QR code as you can see here. And we will have the webinar series 2 on the 11th of May. It's just about 2 weeks later at the same time, 1 to 4 p.m. Thailand time. And the theme will be the power system optimization for capacity expansion planning and sector coupling with Pipesa. So you will hear more about Pipesa for the real case studies and the demonstration about using Pipesa. So I look forward to seeing you all at the next event and have a nice day. Thank you. Bye-bye.
Thank you.
สวัสดีค่ะ
Thank you.
ครับ
สวัสดีค่ะ